Welcome back to the Explainer. Today, we're jumping right into day 10 of our system design syllabus, database indexing. If you've ever wondered how massive, large-scale applications fetch exactly what you need in literal milliseconds without breaking a sweat, well, you're in the right place. We're going to pop the hood and figure out the exact mechanics behind it today.
Okay, let's dive into this. You've probably been there, right? You build this amazing new feature, push it to production, and then you just watch that loading wheel spin endlessly. When a database slows to a crawl, the user experience completely tanks. It's beyond frustrating. Optimizing those slow, bottlenecked queries is exactly the villain we need to defeat today.
Just think about an unoptimized query for a second. To find one specific user, the database essentially has to blindly scan every single row, one by one, through millions of records. I mean, it's sluggish and it's completely unscalable. Our ultimate practice goal for today is the optimized query, achieving instant direct data access. No scanning, no waiting. Just boom, there's your data. So here is our roadmap for the explainer today. 1. The slow query problem. 2. Database indexes. 3. Inside the B tree. 4. Composite indexes. And finally, 5. Execution and optimization. All right, kicking things off with section 1, the slow query problem. The slow query is a major bottleneck in system design. It just drains resources and completely limits your scale. Our source material gives us a very clear, absolutely crucial directive here. Optimize slow database queries. Mastering this isn't just theory, it's essential to ensure your applications can actually handle real-world user traffic. Moving right along to section 2, what are database indexes? So the crucial point is, an index is basically a database structure that dramatically improves your data retrieval speeds. Think of it like the index at the back of a giant textbook. You don't read from page 1 all the way through just to find a specific topic, right? You check the index, get the page number, and flip straight there. A database index does the exact same thing for your data. It's a real game changer.
Let's slow things down a bit and dig deeper in section 3, inside the B tree.
Now, what's really interesting about this slide is that sure, we know what an index does conceptually, but we need to look at the physical mechanics making that lightning speed possible. Enter the B tree. This is the secret engine powering our databases. It's a self-balancing tree data structure that maintains sorted data. Whether you have 10 records or 10 billion, this specific architecture ensures the database can hunt down information in a tiny fraction of the time. Let's walk through this algorithmic journey step by step. First, the search query starts right at the top, at the root node. Then, it compares your search key to the values there and traverses down to the matching child node, literally skipping massive chunks of irrelevant data along the way. Finally, it retrieves your exact data from the bottom leaf node. It's ruthless, precise, and incredibly efficient. Shifting gears to some advanced concepts in section 4, the power of composite indexes. Sometimes indexing just a single column isn't enough for complex system designs. This is where a composite index comes into play. It's an index built on multiple columns in a table to optimize queries that filter on those combined columns simultaneously. Imagine a massive city directory. Searching just the first name leaves you with thousands of Johns. Not super helpful, but searching last name and first name together, that makes your search incredibly targeted and precise. And this brilliantly illustrates how it works in practice. Instead of treating a department search and an employee ID search as two completely isolated operations, the database logically groups these multiple columns into one concrete, searchable structure, a composite index key. So if your system frequently looks for specific employees within specific departments, this combo finds them instantly. Bringing it all together for the finish line in section 5, execution and optimization. Let's break down the chronological journey here. Step 1, the database receives the raw query. Next, the internal engine parses it and plans the most mathematically efficient path. Step 3, and this is where our indexes jump in to save the day, the system actively utilizes those B tree or composite indexes. Finally, it executes the plan, returning the data super fast and eliminating those heavy load times. Let's move to and see how this builds directly back to our main mission. All of the mechanics of the B tree and composite indexes exist for one ultimate reason: query optimization. The goal is to ensure your database engine always chooses the most efficient execution plan possible. Remember, an index is only useful if the execution engine is actually optimized enough to use it. So as you head into your practice phase, keep this checklist in mind. Spot the slow queries causing bottlenecks. Understand the execution plan your database is trying to use. Apply standard B-tree indexes where needed. Leverage composite indexes for your complex filters. And always measure the performance to prove your optimization actually worked. Now that you understand the underlying mechanics of the B-tree and exactly how data is fundamentally retrieved, how will you redesign your systems to ensure a slow query never bottlenecks your users again? You have the tools for instant data access now. Thanks for exploring this with me today, and I'll catch you in the next explainer.